Good morning, everyone. Um, let's continue with the stability analysis. Okay. Just to recall the concepts, what we discussed in the previous class, we started with the stability analysis, right? And the first method was the Hurwitz criteria. So in Hurwitz criteria, you can determine the stability of any linear time invariant system, provided you have the system description in the numerator and denominator polynomial form. All right, fine. Now, in order to apply this Hurwitz criteria, I had also given you the two checkpoints, correct? So the first checkpoint is something like you need to inspect the characteristic equation. In the sense, there shouldn't be any missing coefficients of S term, right? There shouldn't be any missing coefficients of S term. So that is the first requirement. And the second requirement is that there shouldn't be any negative coefficients. Okay, there shouldn't be any negative coefficients. So this is your requirement 2. First requirement is no missing coefficients. Now, if at all the given characteristic equation, if at all it is not suffering from these two uh, no conditions, then you can go ahead with applying the Hurwitz criteria. All right. So today let's look at how to determine the stability using Hurwitz criteria. Okay. So Hurwitz criteria. Now, to start off Hurwitz criteria, okay, let me tell you the step-by-step procedure to apply Hurwitz criteria. Okay, so along with me, even you can start noting down. Okay, so step one, it is a conditional step in the sense if the closed loop transfer function is given, then you can skip off step 1. If it is not given, then you are supposed to find the closed loop transfer function. So step 1 is find the closed loop transfer function. CLTF stands for closed loop transfer function. Now, closed loop transfer function you need to express in a particular form. So we want to express in stability analysis that our transfer function should be there in numerator by denominator polynomial form. Say n of s by d of s. Okay. Let's say our polynomial is of this kind. B naught s to the power n plus b1 s to the power m minus 1 b2 s to the power m minus 2, so on and so forth until you reach the nth coefficient. Okay, that is bn. Similarly, denominator polynomial, let us use different alphabets for the coefficient. A we will take a naught s to the power n plus a1 s to the power n minus 1, so on and so forth, plus bn. Okay. One has to note that n is equal to order of the system. All right. N. What is n? The highest power of s in the denominator polynomial. That is called as order of the system. So that's your step number 1. All right. Next, step number 2. in step number 2, what we have to do is we have to rewrite the characteristic equation, okay, or extract the characteristic equation from step number 1. Let's say, okay, characteristic equation. So let us say the characteristic equation is f of s. So you know that f of s is basically 1 plus g of s into h of s, which is equal to 0. Okay, alright, 0 we will write it later, is equal to, okay, what is the characteristic equation? The denominator polynomial, right? So denominator polynomial is the characteristic equation. So write out the characteristic equation. A naught s to the power 1 n so on and so forth till you reach the last coefficient, which is independent of s, and that is equal to 0. Okay, so that's your step number 2. All right, so you have written the transfer function in step 1, closed loop transfer function in step 1, and you have also written the characteristic equation in step 2. All right, so now let's go to the third step. So from third step onwards, your Hurwitz criteria, calculation starts. So step 3. So you can write the title as creation of Hurwitz determinant. Creation of Hurwitz determinant. So that's your step 3. Now, your Hurwitz determinant, it is denoted by H, and the order of Hurwitz determinant is always of the dimension n cross n, or where n is nothing but order. Order of the system. Alright, where n is order of the system. Now, if say suppose the order is n, then the dimension of Hurwitz determinant will be n cross n. And if you have a third order system, then the order would be 3 cross 3. Okay, so 3 cross 3 determinant you are going to get in case if the order is 3. Alright. Now, how do we create this Hurwitz determinant? So, H is created from the coefficient of f of s. So, Hurwitz determinant is created from the coefficients of f of s. So, what is f of s? The characteristic equation. All right. So, let's see how to create the Hurwitz determinant. Okay. So, you write h here. Okay, and then you draw a big determinant. Big determinant you draw. Okay. I need some space here. All right. Now, the first 2 rows, okay, the first 2 rows of Hurwitz determinant is taken directly from the characteristic equation. Okay, say this is my row 1 and say this is our row 2. All right. So first 2 rows are constructed directly from the characteristic equation. So row 1 is constructed by writing down the odd coefficients. So row 1 is constructed by writing down the odd coefficients. So I'll write coef. And row 2 is constructed by putting the even coefficients of h of s. Okay. Now I want you to look at. Pardon me. Pardon me. Okay. I want you to look at. So first you write down the odd coefficients of the characteristic equation, which are a1, a3, a5, so on and so forth. So the last coefficient will be a2n minus 1. Okay. And then you can write down the even coefficients, which are nothing but the missing coefficients. So even coefficients are a0, a2, a4, so on and so forth. And the last coefficient will be a2n minus 2. Okay. So first two rows are constructed from the coefficients of the characteristic equation. Row 1 is constructed using odd and row 2 is constructed using even. Okay. Once you are done with the first two rows, the third row is constructed by putting the first element of row 3 with 0. Okay. So while constructing row 3, you put the first element as 0 and then repeat the row 1 coefficients, that is a1, a3, a5, so on and so forth. So the last element of row 3 will be a2n minus 3. Okay. And row 4, okay, this is row 3, and row 4 is constructed by putting the first two elements as 0 and then by repeating the row 2 coefficients, that is a0, say a2, so on and so forth, until you reach the last element, which is a2n minus 4. So this process is continued. Okay. So the last element going to be, any guesses? a2n minus 1, a2n minus 2, like this it will go on, a2n minus n. Okay. Now what is this element? a2n minus n is an. Until you reach the last element. So the dimension of this determinant is n cross n. Okay. So first two rows are pretty easy. Row 3, you don't have to calculate anything. Just put this first element as 0 and repeat row 1 coefficients. And for row 4, put first two elements as 0 and then you repeat the row 2 coefficients. Okay, so basically you get something like, triangular matrix, right? In linear algebra, you must have seen the triangular matrix in matrices, upper triangular matrix, lower triangular matrix. So this is what we are trying to create in case of Hurwitz criteria. Okay. Now, once you are done with the creation of Hurwitz determinant, you can apply step 4. Okay. Step 4, and you can write create subdeterminants. Okay. So subdeterminants say dk. Subdeterminants say dk, where k is equal to 1, 2, up till n, where n is equal to order of the system. Okay. Now, what is this subdeterminant? So, as I said, k is basically refers to the order of the system, which varies from 1 to n. Okay. Now, subdeterminants are nothing but the smaller determinants extracted from the Hurwitz determinant. Now, if I take k is equal to 1, I get D1. So D1 refers to 1 cross 1 determinant from the main determinant H. Similarly, D2 refers to 2 cross 2 determinant extracted from the main determinant H. So like this, if I go on, what would be my determinant n? What would be the dimension of dk? So dk, the last value is n. So my last determinant is having a dimension of n cross n. So we had already seen in step 3 that your Hurwitz determinant itself is an n cross n determinant. So dn is nothing but your Hurwitz determinant. Okay. So in step 4, you have to create the subdeterminants of this type: 1 cross 1, 2 cross 2, 3 cross 3, 4 cross 4, so on and so forth until you reach the n cross n determinant. Okay. Once you create these subdeterminants, you can apply step 5. So in step 5, basically you will be checking the stability. So check for stability. Okay. So in the last step, that is step 5, you would be checking for the system stability. Okay. So a system is said to be stable. A system is said to be stable if all subdeterminants, okay, a system, linear time invariant system, is said to be stable if all subdeterminants are positive. Okay. So this is the statement for, condition for stability. If all these subdeterminants gives positive value upon solving, then the system is said to be stable. If any one subdeterminant gives negative value, then the system is said to be unstable. So this is what is your Hurwitz criteria. Okay. So to understand Hurwitz criteria, let us consider a problem. Okay. And with the help of problem, you will be able to understand all these steps. Okay. Nothing to worry. When I explain the theory, sometimes you may feel that the determinant is quite big, but it is pretty easy when you start attempting the problem. All right. So first problem, let us consider. Okay. Take down the problem statement. A system is characterized by the following characteristic equation. A system is characterized by the following characteristic equation given by f of s is equal to s cube plus s square plus s plus 4 is equal to 0. Determine the stability of the system using Hurwitz criteria. Determine the stability of the system using Hurwitz criteria. Normally, such questions will be asked for, typically 6 to 8 marks. Okay. So this is what the question is all about. So you need to determine the stability of the system using Hurwitz criteria. Solution. You don't have to find the transfer function, so you can discard step 1. So you can directly write down, let's say, step 1 as your characteristic equation. So write down the characteristic equation f of s is s cube s square s plus 4 is equal to 0. Now what you have to do is compare this characteristic equation with the standard form. So compare with f of s is equal to, okay. Now in the given system description, you can clearly observe that the highest power of s is 3. That is, n is equal to 3. Okay. So you can write the equation as a naught s to the power 3. Okay, this is your standard equation, right? Which is taken from the standard form. Okay, or the denominator polynomial d of s. So a naught s cube, a1 s squared, a2 s to the power 1 plus a3 is equal to 0. Okay. So what we have done? We have taken down the characteristic equation as it is, and then we have found its order, which is 3. Based on this order, we have rewritten the standard form. Okay. Now you start comparing the powers of s, and then you can extract the coefficients, right? So against s cube, you have a naught as the coefficient, right? So in the characteristic equation, what is the value of a naught? Is 1. So a naught is 1, comma, a1 is also 1, a2 is also 1, and the nth coefficient, which is a3 for our system, a3 is 4. a3 is 4. Okay. So this is your step 1. Okay. And in step 2, you can say that, create Hurwitz determinant. Create the Hurwitz determinant. How will you create the Hurwitz determinant? H is equal to, okay. First you write down the order of the determinant, n cross n, and the highest power of s is 3. So your Hurwitz determinant should be of 3 cross 3 dimension. That means to say 3 rows and 3 columns. Okay. And then you can refer to the standard Hurwitz determinant, and then you can start writing down the coefficients, right? So row 1 you have odd coefficient, and in row 2 you have even coefficient. So odd coefficients are a1, a3, a5, all right, and even coefficients are a0, a2, a4. So first 2 rows we have written with lot much ease, you can say. Okay. And row 3, how will you write? Row 3 is written by putting first element as 0 and then rewriting row 1 element, that is a1, a3. Correct? Now if you check your main determinant, okay, which I had given in the earlier discussion, the last coefficient is always an, correct? Last coefficient is always an, and in our system, power of n, or the highest power of s, is 3. So we are supposed to get a3 as our last element, and the same thing we have obtained. Okay. So you can say that you have successfully applied the logic while creating the Hurwitz determinant. All right. So once you write down the Hurwitz determinant, things will be lot easier to deal with. Okay. Next you write subdeterminants. Subdeterminants. Dk, where k is equal to 1, 2, 3. That's because n is equal to 3. So how many subdeterminants we are going to have? We are going to have 3 subdeterminants. That is D1, D2 and D3. Okay. So D1 you can directly find from your n cross n determinant. So this is your D1, 1 cross 1. Alright. And this is your D2, 2 cross 2. And D3 will be your Hurwitz determinant itself. So D1 is basically, what is it? 1 cross 1 dimension. So if you try to find the 1 cross 1 determinant from your Hurwitz determinant H, you will get A1 as your first determinant, subdeterminant, sorry. And your second subdeterminant is, what is it? A1, A3, A0, A2. A1, A3, A0, A2. And your third subdeterminant happens to be D3, which is nothing but your Hurwitz determinant. And the elements are already expressed. A1, A3, A5, A0, A2, A4, and 0, A1, A3. Okay. So this is how you write down the or create the subdeterminants. Okay. So you have already written, right, the coefficient values. Now what you have to do is you have to just substitute the coefficient value. I guess A2 is also 1 and A3 was 4. Okay, that's all. Write down first D1. What is D1? D1 is A1. And what is A1? Is 1. Okay. And solve this. It's a 1 cross 1 determinant. So D1 value, you will get it as 1 itself. And as a comment, you can write positive value. So when you evaluate this 1 cross 1 determinant, you will get the value of the determinant as plus 1, so which is a positive value. Next, you try finding out D2. And what is D2? It's a 2 cross 2 determinant. And what are the elements of determinants? A1. What is A1? Is unity. A3. What is A3? Is 4. A0. What is A0? Is unity. A2. What is A2? Is 1. So this is your 2 cross 2 determinant, right? Solve this determinant and tell me what value you will get. So how do you solve cross multiplication, right? Principal diagonal, 1 into 1 minus 1 into 4. So basically it is 1 minus 4. And what do you get? The value of the determinant as minus 3. So negative sign, right? So negative value. You can write negative value. So D1 you have evaluated, D2 you have evaluated. Now let's evaluate D3. So before evaluating D3, first let us construct D3. Okay. So D3 is consisting of A1, A3, that is 1, 4. Okay. What is A5? Do we have any information of A5? No information. No information means 0. Next, A0, A2. That is also 1 and 1. And A4, there is no coefficient such as A4. If you don't have coefficient, put it as 0. And then you have 0, A1, which is unity, and A3. What is A3? A3 is 4. Okay. Done. Okay. Now you need to solve this 3 cross 3 determinant. Okay. I hope you remember. Okay, so how will you solve? You can find D3 is equal to. Okay. So you have to use that matrix sign, plus minus plus. Okay. Minus plus minus and plus minus plus. So basically 1 into 4 minus 1 into 0, which is 0. Okay. Then minus sign. Minus 4 into 1 into 4. Sorry, minus 1 into 4. Sorry, 1 into 4. Correct. Zero into 0. Yeah. Minus 0. Plus 0 into 1 into 1 minus 0. Okay. So that is equal to 4 minus 8 minus 16. Sorry. Okay. Plus 0. So basically you will get minus 12. What is minus 12? Again, it's a negative value. Okay. Tell me about the system stability. We had stated earlier that in case of Hurwitz stability criteria, a system is said to be stable if all the subdeterminants are positive. But in our case, only one subdeterminant is positive, rest two are negative. Hence, you can say that since two subdeterminants are negative, the system is said to be unstable. System is said to be unstable. Unstable. Okay. So this is what is all about the Hurwitz determinant. Okay. So you can talk about the drawbacks straight away. You can handle the system at the maximum a third order one, right? Because you can easily solve 3 cross 3 determinant. What if the order of the system is greater than 3? Say suppose you have order 5. So if the system order is 5, then you will have a 5 cross 5 determinant. How will you solve a 5 cross 5 determinant? Very difficult, right? Unless or otherwise you have some computing tools such as MATLAB. So for handheld calculation, this is the maximum order we can handle, that is 3. So one of the major drawback of Hurwitz criteria is that as the order of the system increases, the complexity is also increasing in nature. Okay. So Hurwitz determinant or Hurwitz determinant method is applicable to higher order system till the order is 3. Okay, only till 3 or the third order systems can be analyzed using Hurwitz criteria. Higher order systems are very difficult to analyze with Hurwitz criteria. Fine. So from the Hurwitz criteria, we saw that two subdeterminant values are negative, and hence you could say the system is unstable. Okay. Whether it is right or wrong, who is going to tell me? So you can always do a quick cross check. Okay. So what is the system order? It's a third order system, right? So it is s cube plus s square plus s plus 4 is equal to 0. It's a third order equation. So you can use your calculator to find the roots of the characteristic equation. So when you find the roots, you are supposed to get 3 roots because it's a third order system, right? S1, 2, 3. Okay. So I want you to put this equation in your calculator and I want you to tell me the root value. Okay. Okay. So when you cross check using your calculator, just tell me if I am wrong. S1, 2, 3, you will get it as minus 1.743 as the first root, and the remaining two roots are complex conjugate whose value is 0.3714 plus or minus j 1.4686. Are you getting this? Now, what are these roots basically? The roots of the characteristic equation are also called as closed loop poles. Closed loop poles. Now, if I were to place these closed loop poles in a complex S plane, okay, in a complex S plane, you will get the pole 0 plot plus j omega minus j omega. Okay, so let me place these poles. So my first pole is located at minus 1.743. So I can say minus 1.743, which is LHS of the S plane. What about my two poles? Where is its location? The imaginary part is plus or minus j 1.47, you can say. So j 1.47 and minus j 1.47. What about its real part? Where is it? Where the real part is located? It is located on RHS of the S plane, which is at 0.37. So 0.37, let's say somewhere over here. 0.37. Okay. So this is j 1.47. Okay, I'm just approximating. And this is j minus j 1.47. So these are my remaining two roots. As you can clearly observe that out of three roots, two roots are found on RHS of the S plane. Okay. So this is your RHS of the S plane. So in RHS of the S plane, what do you get the system stability as? Unstable. So in the stability region, we have seen that right hand side of the S plane is unstable region. Only the left hand side of the S plane is stable in nature. Okay. So you can cross check with finding out the closed loop poles. If any one closed loop pole is present on RHS of the S plane, you can call it as unstable. So Hurwitz criteria result is fitting well with the conventional approach, that is physically solving the roots of the characteristic equation. All right. So you can say that both the methods are giving consistent results. Okay. So this way you can cross check your answer. All right. Fine. So that's about Hurwitz criteria. Okay. Problem number 2. Let's consider. Okay. Let's say you have the characteristic equation of the order write down. Okay. Given that f of s is equal to s cube plus s square minus s plus 4 is equal to 0. S cube plus s square minus s plus 4 is equal to 0. Determine the stability using Hurwitz criteria. Determine the stability using Hurwitz criteria. Can anyone tell me? Do I have to apply Hurwitz criteria here? I don't have to apply Hurwitz criteria because the coefficient of s to the power 1 is negative. So you can write observation coefficient of s to the power 1 is negative 1. So as per the stability requirement, the coefficient of s term shouldn't be negative. But in a given characteristic equation, you have obtained the coefficient of s to the power 1 is negative. Hence, you can directly say that system is unstable. You don't have to apply Hurwitz criteria for this. Directly you can say system is unstable since s to the power 1 coefficient is negative. Okay. If you want, you can do cross check. Okay, how do you do cross check? Try finding out the roots of the characteristic equation using your calculator. When you do that, you will get s1, 2, 3 is equal to minus 2.241, comma 0.62 plus or minus j 1.1826. Okay. So this is what you get as the closed loop location. So one is located at LHS. So this is located at LHS, which is good for stability. But what about the remaining two roots? This is having positive real part, right? So this particular complex conjugate root is having positive real part, due to which you can say that system is unstable. Okay. Please, about this stability region, please refer the previous video about stability. In the previous video, we have discussed about the stability region for system stability. Okay. So this is one special case for Hurwitz criteria, wherein you don't have to create the determinants. You can say that the system is unstable with the help of inspection method, which I have discussed just now. All right, fine. So this is about, say, category 2 type problems. Okay. Say category 3, let's take. Yeah. Let's say I have the system description, something like this: s cube plus s plus 4 is equal to 0. Okay. Let's say we have a system of the given characteristic equation: s cube plus s plus 4 is equal to 0. And let's say you have been asked to find the stability using Hurwitz criteria. Question is, are you going to apply Hurwitz criteria? Your answer should be no. Why? Because in the given characteristic equation, you can say that s square term is missing. Okay. As per the, to apply Hurwitz criteria, there are some prerequisites have to be met, right? So prerequisites have to be met. See, one of the prerequisites is something like there shouldn't be any missing s terms, right? So over here you have a square term missing in the characteristic equation. Hence you can directly say that system is unstable due to the missing term, which is s square in our case. Okay. You can also do cross check. A quick cross check is always advisable. Okay. When you substitute this equation in your calculator, okay, again it's a third order equation, so you must get 3 roots: s, 1, 2, 3. So when you solve this particular equation, the closed loop poles, you will get it as minus 1.378, comma, again complex conjugate root 0.689 plus or minus j 1.55. As you can clearly observe, out of three roots, a pair of roots are having positive real part, right? So this is having positive real part, hence you can say system is unstable. For stability, you would want that all the closed loop poles of the characteristic equation are present on LHS of the S plane. Okay. But here, out of three roots, two are present on right hand side of the S plane. Hence, you can directly say the system is unstable. All right. So, more than advantages, your Hurwitz criteria has disadvantage. The biggest disadvantage is higher order systems cannot be checked. So you cannot judge the stability of higher order systems. So this particular drawback of judging the stability of higher order systems is overcome using a modified Hurwitz method, which was proposed by mathematician Ruth. Hence, it is called as Ruth-Hurwitz criteria. So tomorrow, let's talk about Ruth-Hurwitz criteria. So Ruth-Hurwitz criteria basically helps in finding the stability of higher order system. So any given system, the order may be 20, 21, 22, whatever it may be. Okay, you can solve using RH criteria or Ruth-Hurwitz criteria. Okay. So if you have any doubts, you can just discuss.